Next in our study of reasoning and proof is the study of conditional statements. Now, a majority of what we're going to be working with will be based on these statements. The way they are written is that they take on the following form, and that is P, Q, with the arrow in between. The way this reads is if P, then Q. Now, P is called the hypothesis portion of the statement. Q is the conclusion. So if our hypothesis holds true, then the conclusion must be reached. An example for this. If an angle measures 130 degrees, then it is obtuse. The opening portion, an angle measures 130 degrees, is the hypothesis. The conclusion, the angle is obtuse. Now we take those individual statements and put them together into our conditional. Now, there are possibilities that in the realm of all the conclusions, there is a subset of that completely contained in it that are the hypothesis. An example here, there are a lot of angles that are 130 degrees. A lot of angles that are obtuse. The 130 degrees is a small portion of those. So it is possible to have the conclusion met without having gone through the hypothesis, simply because we took another route. And when we write these, we have to pay attention to what is what part. Simple statements or definitions can also be conditional statements, such as squares are quadrilaterals. This is a simple definition or part of a descriptor for squares, but how could we make this into a conditional statement? We could say if an object is a square, that's my hypothesis, then it is a quadrilateral. That acts as the conclusion. So take a simple statement, make an if portion, and then a conclusion portion. And you will begin to have this idea of your conditional statements. So when we have conditional statements, we need to look at the validity of them. We could have a conditional that can be met or a conditional that cannot. And for this, we work with something called truth tables. Truth tables, simply put, are a way of metering out if our conditional statement has been met. So when we're working with truth tables, all we have to do is determine if an item is true or false. Typically, if false, we're then also going to find a counterexample to justify our decision. So if a number ends with 0, it has 5 as a factor. Is this true or false? Well, we know that all multiples of 5 end in either 5 or 0, so if it ends in 0, it could be divided by 5. This is true. If a month contains 28 days, then the month is February. On surface, this one looks true, but if you think about it, all months contain 28 days. January has 28 days plus an extra 3. So that would be an exception to this rule, and it is false. So January does contain 28 days, it just contains a few extra on top of that. And this is all we do for truth tables. Determine if the statement is true or false, and remember it has to be true in all cases. Do all months that contain 28 days, are they all February? No, because all 12 months contain 28 days and they're all named something different. But all numbers that end in a 0 have 5 as one of their factors. So along with these truth tables, there are other types of writings and notations that are used in logic and proof arguments. And we're going to take a look at those and then see how truth tables related to all these different relations. So we're going to begin with negation. And with this, we're using the same P and Q ideas. So if I have a negated item, meaning that I'm turning it from a positive to a negative, I simply write not P. The tilde symbol shows not. Converse. And remember, all these were based off of if P, then Q. So for a converse statement, what we do is we reverse our hypothesis and our conclusion. So converse reads, if Q, then P. An inverse is when we negate both items. So we say, if not P, then not Q. And the last one we're looking at is the contrapositive. A contrapositive is the inverse of a converse. So what that means is, if not Q, then not P. So we switch our hypothesis and conclusion, and we put a negation on both of them. So let's take a look at what this would be like with actual items. So the statements we're going to be working with, our P statement is an animal is an herbivore. Our Q statement is an animal eats vegetables. And I'm going to go through and look at each of these statements and determine their validity. So let's begin with our base conditional statement. If P, then Q. So if an animal is an herbivore, then the animal eats vegetables. And this is true. That is really the definition of an herbivore. Next, we're going to try the converse, which states if Q, then P. So if an animal eats vegetables, then the animal is an herbivore. And this is false. The example we're going to use is an omnivore. An omnivore means eats all things. So an omnivore eats both meat and vegetables, therefore it still qualifies without being an herbivore. Next up, we're going to have our inverse, which states if not P, then not Q. So if an animal is not an herbivore, then the animal does not eat vegetables. And again, this is false because of the omnivores. Omnivores are not herbivores, but they do eat vegetables. So same reason as before. And last is our contrapositive. If not Q, then not P. So if an animal does not eat vegetables, then an animal is not an herbivore. And this is true, because if an animal doesn't eat vegetables, then that goes contrary or against the definition of herbivore. So when you have these four types of statements, the conditional, converse, inverse, and contrapositive, you will always find this same pattern. If the conditional is true, then the contrapositive is true. If the converse is false, then the inverse is false as well. The ideas play off of each other. So a lot of new vocabulary here, and it's going to be the basis of our logic and reasoning, and establishing proofs in geometry. Make sure you have these ideas down and are ready to use them.